vote something about special relativity. Okay, so you know about relative motion. Here's a simple problem. There's a car going 40 meters per second, and you're in the passenger seat of the car, and you throw a ball like forward out the window, 10 meters per second. How fast would somebody standing alongside the road say the ball is going relative to the road? 50 meters per second. Yep. So, like, if the car is at rest and you throw a ball out at 10, it's just going 10. If the ball is sitting in the car and the car is going 40, the ball's going 40. But if the car is moving and you throw the ball, you just add up the speed. So you'd say the speed of the ball relative to the ground would be 50. You just add them up. That's called Galilean relativity, or just classical relativity. But here's where things get complex really fast. So what if you have a car that is moving along, that was kind of a mess, at 40 meters per second, and you turn on the headlights so that the light goes out of the front of the car. Now, if you're sitting still and you turn on the headlights, the light goes out at the speed of light. If you're driving along and you turn on the headlights, if it's something like the ball, then it's like the light would have to leave going the speed of light plus 40 meters per second. And there's a big problem with that. And that's that no matter how and when you observe light, it always travels at the same speed in any particular medium. So there's a conundrum. How is it that the light will go at the speed of light, the same speed, relative to an outside observer who's like chilling out here, or to the person in the car? In other words, the person in the car would say the light is going out of the car going at the speed of light, and the person standing alongside would say as that light goes by, it also goes at the speed of light. It's almost as if like the 40 meters per second doesn't matter. This is it's like a philosophical problem and a mathematical problem, sort of. Like, what's the reality? So here's another situation. What if this is a school bus? You can try this if you don't believe me. You're sitting in a bus, and the bus is moving along at 40 meters per second. And you take a ball and you toss the ball straight up. If while the bus is going at a constant speed, you toss the ball straight up, what does the ball do relative to you? Yeah, right back down into your hand. Because otherwise, imagine if it were that like tossing a ball up, it would, yeah, it would be independent of motion. Taking a brick and just tossing it over back to the back window. Yeah, it'd be dangerous. It'd be deadly. It'd be like, okay, one of the first things you got to teach your kids is, okay, when we're in the car, don't drop anything or toss anything because it's going to go through a window or something. That's not how it works. Now, the issue is that if you're sitting in the bus and you toss that ball up in the air, it just goes up and down and up and down. You can just play catch with yourself. It doesn't matter. But what would a person outside of the bus observe that ball to do? Yeah. So what would the motion of the ball be relative to the ground? Like an arc. It would be a projectile because you give it an initial vertical velocity. It goes up and it comes down, and at the same time, it moves forward at constant speed. So in the time that it takes for the ball to go up and down, let's say the bus has moved forward some distance. I'm going to exaggerate this. And now the bus is out here. The ball's tossed up here and it lands here. The motion of the ball is like that of a projectile to the person standing outside the bus. So what is the ball doing? Well, it is both being tossed up and come straight down relative to the viewpoint of the observer in the bus. Somebody outside the bus, it actually acts as a projectile. And both of those things are totally okay. That's completely in the realm of reality. So this is a problem that kind of vexed physicists for a long time. And then a real smart nerd comes along who we have never talked about in this entire course, but is the most famous physicist ever, probably, Albert Einstein. So Albert Einstein was born in like 1879, I think, in the late 1800s in Germany, and lived in Switzerland for a while. Ended up coming to the United States on visits for a couple different reasons. ended up making a trip in 1933 to the United States, and that's actually when Hitler took power, and that's when Einstein's like, I'm staying. I'm good. So then he stayed in the United States, came here in 1933, became a citizen in 1944, and stayed in the United States until his death. And he gave a lot to us in physics. He had a really good year, one year, the year 1905. It's called the Miracle Year. And that miracle year, he published 4 papers: one on Brownian motion, one on the photoelectric effect, which he won the Nobel Prize for, one on special relativity, and then one on the equivalence principle. That's the formula like E equals mc squared. Each of those 4 contributions in physics was on its own one of the most remarkable things you could have ever said. And Einstein's like, yo, I did all this stuff in 1 year, just for LOLs, while he was working at the Swiss Patent Office. And he was quite young. So the problem that he took up was this problem about what would the behavior of light be if it was like the ball in the school bus thing. So here's the problem. The way that he wrote it, and honestly, like one of the best ways to even do the math in the first place. At the time in 1905, like the fastest thing is really a train. Like it's early, and automobiles and cars didn't really go fast, and we didn't have like school buses like that. There were no airplanes. So Einstein famously wrote and drew this problem as if it's in a train. So here's a train car, and we still use the train car analogy. So one of the things about this problem is, what if you are just inside a train car and you don't know what's going on in the world outside you, but in that train car you have like a light, like a flashlight, and then there's a mirror on the ceiling, and you turn on that flashlight, and the light from the flashlight goes from the light up to the ceiling, and it comes back down. Now, you should agree that no matter if the train is at rest or if the train is like cruising along on the track, if you point that light straight up and it hits a mirror, it'll come right back down. So just like a ball, you toss the ball up and you catch it, that light's going to go up and down. But, and I'm going to exaggerate it here in this case too, because it's not going to be like that. What if the train is actually moving? The train has some kind of a velocity. If the train has a velocity, to the person in the train, the light goes straight up and straight down. But in the time it takes the light to get from the light bulb up to the ceiling and back down, the train has moved forward some distance. So where the light hits isn't here in space, but it's somewhere else in space. When I use space, I mean like outer space. I mean just like in this reference frame. And I'm going to exaggerate this because I've got this train going faster than the speed of light, but it makes it for the math to be easy. So in a way, let's say you turn the light on here, and the light first leaves the light bulb, but the train is moving in this direction, and here I've exaggerated it just for the sense of this diagram. The train is going faster than the speed of light, but it's not really going faster than the speed of light. The light leaves here, and in the time it takes for the light to get back down to the light bulb, the train has translated over to this position. So that means that the mirror is like here when the light hits it, and the light comes back down to the flashlight when it's at this position. So the real motion, there's 2 motions for the light. The motion of the light relative to the person inside the train is straight up and straight down. But to somebody outside observing, who's an outside observer, the light actually travels like this. It's actually simpler than the problem of tossing a ball up and having it fall down. When you have an outside observer watching the ball being tossed up and down because it's a projectile, and you got motion, that's linear and squared. Yep. But now the problem is just constant speed. All right, here's the biggest misconception about Albert Einstein. Well, people say things about Albert Einstein that aren't true. People may mishear things about Einstein. One of the biggest myths about Einstein that you hear is people say that he was like bad at math. And that's pretty insane because you don't get a PhD in physics if you're bad at math. You just can't do that. It's like it's the same as saying, "Oh, I know somebody who has a PhD in English and they don't know the alphabet." Like that's not a thing. It doesn't make any sense. You just don't get there that way. But one reason why the misconception can come about is because of a proof that's as simple as this. I'm going to make a triangle here. And get this nice right triangle. Like we'll just deal with this left right triangle here. There are dimensions. There is the vertical distance from the light bulb to the mirror, call that y. There's this horizontal distance that the train moves in getting from here to here, call that x. And then you have this hypotenuse. So Einstein was like this. He's like, okay, to the person in the train, the light only travels up and down, or it goes up to the mirror a distance y. To the person standing outside the train, the light travels from the light bulb to the top of the mirror along the hypotenuse. And in that same time, the train moves a horizontal distance x. So Einstein's like, could it be so simple as just starting with the Pythagorean theorem and just plugging in the distances? The distance the light goes up and down inside the train, according to the person inside the train. Yep. Because the light goes to the mirror kind of two ways. Do you see? The light only goes up to the top of the train and back down, according to the person inside the train. The person outside the train, the light goes from here to here. And at the same time, the train goes this far. It's just the Pythagorean theorem. So uh, here's how it goes. When you have the Pythagorean theorem, we'll say like x squared plus y squared is equal to that hypotenuse squared. The horizontal distance that the train travels. So all you need to do, honestly, all you need to prove special relativity and do one of the papers that Einstein did in 1905 is the definition for velocity and the Pythagorean theorem. That is all the math you need, period. And you get to be the person who invents special relativity, not Einstein. You also have to go back 117 years and do it. And it's kind of amazing that no one did this before Einstein. So in this, the velocity is distance over time, or distance is equal to velocity times time. All right, so here's the deal. The horizontal distance the train travels is equal to the speed of the train times the time. This v is the speed of the train, and that's the time it takes for light to get up to the top. But I only want to do it for half this triangle, so the x or vt over 2 represents there's a reason for this, the distance that the light travels only getting up to the top, where t is the round trip time from bottom to top and down. I just want to do from the bottom to the top because the Pythagorean theorem can only be half the triangle. Plus the vertical distance, which is just y. It's the height of the train. And the hypotenuse is equal to the path that the light actually travels. And the path the light actually travels, according to the outside observer, is along this dotted green line. And the speed of the light isn't the speed of the train, but it's the speed of light itself. We use the symbol c to represent the speed of light. The speed of light is 3 times 10 to the 8th meters per second. It's good to three significant figures. We kind of, I don't want to say got lucky, but the metric system was developed independent of the speed of light, and it turns out to three significant figures. The speed of light is 3.00 times 10 to the 8th meter per second. We call that c. So the hypotenuse is ct over 2 squared. So this vt over 2 represents the distance the light travels horizontally. The y represents the distance the light travels up and down, and the ct squared over 2 represents the distance from the light up to the top along the path the light actually travels according to the outside observer. And so that's it. And you got to do a little bit of algebra now. So that's what Einstein did, and then he does some algebra. So what I want to do is square all this crap. So it goes v squared t squared over 2 plus y squared. Oh, not over 2, over 4 plus y squared is equal to c squared t squared over 4. I want to group these terms that have the time in it. So it goes v squared t squared over 4 minus c squared t squared over 4 is equal to uh, negative y squared. But here's a little trick, like a little hand waving. It doesn't have to be negative y squared because anytime you square something, it just becomes positive anyway. But what I want to do now is factor the t's out and multiply both sides by 4. So if you factor the t's out, you get t squared times c squared. Oh, I know. Here, I can just make them, I can just change the sign of all of them. I'll do that first. This will make things easier. In other words, if I just change the sign of everything, it becomes, uh, well, I'll do c squared t squared over 4 minus v squared t squared over 4 is equal to y squared. So I just made the signs opposite. I can factor out t squared and multiply both sides by 4. There's a reason for that. And then divide both sides by c squared and v squared. So you end up with t squared is equal to 4y squared over c squared minus v squared. And then what you do is you take the square root of everything. And when you take the square root of everything, you end up with t is equal to 2y over, I'm going to write it as the square root, there's a reason for this, square root of c squared minus v squared. And it might look like it's getting better, but I'm going to make something messy, and that's on purpose. I'm going to actually factor out a c squared from inside. And this is with a little bit of hand waving, kind of like it doesn't seem like you should want to do this, but I'll show you why it happens. If I factor out c squared, the square root of c squared is just a c. You get c, and then 1 minus v squared over c squared. This is the order in which the proof kind of happens. Now, another thing that we got to deal with is when this light goes from the light bulb up to the mirror and back, according to the person inside the train, it takes some time for the light to go up and down. And that person inside the train measures some time. It's called the proper time. And I'll give you a paper that talks about that. T sub p stands for proper. And a proper time or proper velocity or proper mass is the time, the mass, or the velocity if you're traveling with the thing. So like you're in the train with that light doing that, that's the proper time. The person out here is just time. What I'm getting to is that this person inside the train and this person outside the train, they won't agree as to how much time it takes for the light to do this. It turns out that's the actual solution. Because it seems like the light goes two different distances at the same speed, which is impossible. And Einstein was like, you can make it possible if the rate of passage of time is different for the two different people. The light can go a greater distance for the person outside if you just give it more time going at the same speed. So the genius is, well, the rate of passage of time doesn't have to be fixed or the same for everybody. The rate of passage of time can be different depending upon how fast you go.
Absolute value, that's the speed of time, no matter what's going around it. That's how fast it's going to go.
Yep. So this proper time is 2y over c for the round trip from here up to the top and bottom. The reason why you want to make this formula say t is equal to 2y over c times the square root of 1 minus v squared over c squared is because this idea of proper time is equal to 2y over c. What Einstein actually did is said, listen, I got this proper time as 2y over c. How can I put this formula together with this formula to get rid of the height of the train and express this just in terms of the amounts of time? So do you see how there's 2y over c here? There's also a 2y over c here. You end up with this expression, time is equal to proper time over the square root of 1 minus v squared over c squared. And this expression is the expression for what we call time dilation. To dilate means to make larger, means to make bigger. If your pupils are dilated, they're larger than they ought to be. The reality is the person inside the train will say, it takes so long for the light to get from the light bulb to the top and back down, and the distance is shorter. So at any speed, the time's going to have to be less. But to the person outside, they will not agree as to the time that it takes for the light to get from here to here, because traveling at that fixed speed and the light has to go a greater distance, it's going to have to take more time. The times won't match. The stopwatches won't match. Faster you go, the faster time passes for you. And for someone who's stationary relative to you, the longer the time will take. Time is not a fixed thing.
So
Time is relative.
Train, and the train like this, the train is going twice the speed of light.
Well, it can't go that fast.
It can, but
yep.
Like with that arc of how the time goes up, it hits the pier and it comes back down. To somebody standing like outside, you look like you're going slower, but when you're in the train, you perceive yourself being faster.
That's right. If you have stopwatches, they won't agree.
Yeah.
Here's a famous experiment. You want to prove that's to be true, you got to do an experiment. So, if I'm spelling that wrong. Let's find it. Oh no, I did. Hateful Keating experiment. It's a famous experiment. So, what you do is you get yourself a highly precise atomic clock. You buy yourself some seats on an airline, and you take off from an airport. You fly at a high speed around the Earth, and you get back and you look to see if your clocks are in sync. And the clock that was on board an airplane traveling at not even near the speed of light, but at a high speed for a long enough time, the amount of time that has passed on the clock that took the flight is less than the time the clock sat still at the airport. So in other words, you can have two atomic clocks that are precise to incredible precision for long periods of time, and they will agree absolutely as long as they're sitting next to each other.
Take one in a plane around the world.
Yep.
That one, sort of time dilation.
Yep. The one that sits still says the one that was gone for longer than the one that was gone said that it was gone for.
Yeah.
The modern problem for this.
The speed of light has to be the speed of light, and it influences everything around it. It's true.
Yeah. And also, in a funny way, light takes no time to actually do its own travel. So we say it takes time for light to get here from the sun, but to the light itself, it takes no time. The most practical example of this is in your pocket.
Oh, yeah,
you got a cell phone, and that cell phone relies upon GPS satellites. And all that a GPS satellite is a highly precise atomic clock sending a radio signal to the Earth, telling everybody on Earth where the satellite is and what time it is. And those atomic clocks aboard those satellites never lose any kind of accuracy or precision as long as they're sitting on Earth. But as soon as you put those clocks in orbit and they're cruising around the Earth going really fast, they have to be recalibrated daily.
Really? Wow.
Yes, on Earth they're perfect for, I don't know, 1 million years if you want. But you put the thing in orbit, make it go fast, and it ends up the rate of passage of time is different. There's another problem too, and that's a later problem that Einstein described in general relativity, where gravitational fields are also accelerating reference frames. So the rate of passage of time is also different when you're closer to the Earth than when you're further away from the Earth, but that's a separate issue. So just the fact that you're moving fast, the rate of passage of time is different for you than for someone else. There's a problem. The most famous problem or description of this is a thing called the twin paradox. If you want to read some good stuff, and the twin paradox goes like this: you have two identical twins, maybe born on the same day at the same hour. One becomes an astronaut. It turns out that we actually have identical twin astronauts in NASA. I don't know if you know, Mark Kelly and his brother. I don't remember. One of them is named, or one of them was married to Gabby Giffords, who was the Arizona congressperson. She was like at a campaign rally and got like shot in the head and almost died of it, and it was really messed up. Anyway, they've both been to space and whatnot. So actually, one did a long duration space trip aboard the International Space Station, and one of the nice things is he has an identical twin brother on Earth, so you can look to see changes biologically. But it goes like this: one astronaut, the other astronaut, they're the same age. This astronaut gets on board a spaceship and travels at a very high rate of speed out to some distant star and then travels back. That the astronaut who traveled at a high speed away and came back, when they return to Earth, they will not have aged as much as their twin. Now, for like going to the International Space Station, going on the Earth and coming back, it's an immeasurable amount of time. It's measurable, but it's an insignificant amount of time. It's not a big deal. But if you're talking about like interstellar travel over long periods of time, this is kind of a big issue. So the twin paradox goes that the twin who comes back is actually younger than the one who stayed on Earth. One of the limits with potential interstellar travel happens to be that the further away something is, the faster you want to go to get there. But the problem is the longer on Earth it takes for the person to return. So that could be a practical matter. All right, so how it works is I'll go back to this. This is the formula for time dilation. So let's say the train is only going 20 meters per second. How much of a difference does this make? Well, it has to do with what this factor in the denominator is. If you take the square root of 1 minus 20 squared over 3 times 10 to the 8th squared. So just this second part here, 20 squared divided by 3 times 10 to the 8th squared. Well, 20 squared is about 10 to the 2, and the denominator is like 10 to the 16th. So it's like 10 to the 2 over 10 to the 16th, which is like 10 to the negative 14th. 1 minus 10 to the negative 14th is pretty much still 1, and the square root of 1 is just 1. So the denominator really doesn't change. For low speed things, this doesn't make any bit of difference. What you do care about is for things that are going much faster. So here's an example. We'll do this. What if this spaceship is traveling at half the speed of light? We'll say 0.5 c. In other words, the speed of light is c. The speed of the spaceship is 0.5 c. So t is equal to t sub p over 1 minus v squared over c squared. You don't have to substitute values that are actually in meters per second because this is a ratio. You can do it in fractions of the speed of light. So let's say that the person on board the spaceship thinks or says the trip takes like 3 years. This is for the person on board the spaceship. You could go 3 years divided by 1 minus 0.5 c squared, or just 0.5 squared. And if that's just c, it's just 1 c squared. So really this is actually just 3 over 1 minus 0.5 squared over 1 squared. And 1 squared is just 1. So if you do it in terms of the speed of light itself, you don't have to kind of worry about this. Okay, 0.5 squared is 0.25. 1 minus 0.25 is 0.75. And the square root of 0.75 is 0.866. So this is like 3 over 0.866, which is 3.64 years. In other words, the person on board the spaceship, according to a clock on board the spaceship, or like their watch, it's a 3-year trip there and back. But to the person here on Earth, it's 3.46 years.
0.5/1.
Here's one way to conceptualize that. Let me ask you this. When this person on board the spaceship gets to that distant planet, they might radio back to Earth and say, I'm here. But when on Earth do we find out they're there?
When the radio signal gets there.
Whenever the radio signal gets back to us. You know what I'm saying?
Yeah.
So you have this issue of simultaneity. You're like, or even from Earth, as you watch this person travel away, they would measure it to be 3 years, but as you watch them travel, the further they get, the more time it takes for the light to get back. Yeah, so you can see how this is actually realistic, right? Like, when they actually get there, we can't see that they're there.
We see the light that was left behind.
Yeah, we have to wait for that light to get back to us, right? So we can't see them arrive when they arrive. We see them arrive after they've arrived. They've already gotten there. So there's already a difference in the time, you know?
But when they're coming towards us, there's no acceleration of that light.
No, but there's still a problem because the moment you see them take off, they've already taken off and they're already on the way, right? So the time you think it takes for them to get back is longer than the time they actually spend traveling, right? So that you don't have to know special relativity. You just have to consider, like, it takes time for the light or for the signal to even get there. So what if instead it's half a c? What if we're like, we want to make the trip even faster? Let's go at a speed of like 97% the speed of light. And that trip won't take 3 years. It'll only take like about a year and a half, right? Because if we about double the speed, we're only going to take like half the time. So if the proper time is not 3 years, we're like, listen, this 3-year round trip is too long. We got to get these people back sooner. How are we going to get them back sooner? We're going to make them go faster. If we make them go faster,
They come back.
yeah, the thing is they'll say, oh, good, my trip's not going to be 3 years. It's only going to be a year and a half because I can go twice as fast. But here's the irony to it. The time that you would measure for them to take is 1.5 year divided by 1 minus 0.97 c squared over 1c squared. And now this denominator is completely different. 0.97 squared, 1 minus 0.97 squared, square root of that is 0.243. In other words, this denominator is equal to 0.243, 6.17 year. So here's what's crazy. If you send these people at half the speed of light, they're like, my trip took me 3 years. We had to wait 3.46 for them to get back. If instead, we're like, we're going to get you to go almost the speed of light, 0.97 speed of light, 97% speed of light, you will only think it takes a year and a half. So you're going to have like a year and a half of food, a year and a half of oxygen, a year and a half of water. But they won't get back for 6.17 years.
The faster they go, the slower they come back.
Yeah.
What's is there like a Goldilocks speed for them to go back and come within like the least amount of time for you?
Well, see, so the problem is as
time dilation was happening, so the slower the better, technically.
Yeah.
So the time doesn't match up. You're slower, but
Yeah, the time for the stationary observer and the moving observer grow to be larger and larger and larger. They become more disparate. And as the speed approaches the speed of light, they become infinitely great relative to each other. It takes 8 minutes for the light to get from the sun to the Earth. But to the light leaving the Earth, or leaving the sun, it takes 0 time. Because it's 1 over 1, and 1 minus 1 over 1 is 0, but it's not. It's the square root of 0, which is not a thing, but as you approach the square root of 0, this denominator approaches 0, and as the denominator approaches 0, the time is infinitely large as compared to the time it takes for the light itself. So light takes no time to get anywhere. When we observe the Big Bang 13 billion years ago as the light leaving the edge of the universe, that light actually takes no time to get to the Earth, but has spent, according to us, 13 billion years getting here.
Yeah.
But that's also kind of cool because it's.
So if the Big Bang happens and then it causes some planets to be formed, and millions of years later, the people on that planet are studying the Big Bang, they're looking at that light. The light took no time to get from the middle of the Big Bang to that planet.
Yeah. Well, see, as the universe ages, more space is made.
Yeah.
And somebody says, well, where did the Big Bang happen? Well, it happened. It happened. And it is the whole universe. And no matter which direction you look, you see the remnant of the Big Bang, because in all directions it's in the age of the universe away. Yeah. So you are the center of your own universe. As you measure things, you are, like, if somebody, to be honest, if somebody says, what do you think, you're the middle of the universe? Say,
Yes.
yeah, and so are all points.
So
You know?
they also consider enough time to get to you, right?
That's right. No matter where you go, we observe it's a problem, a neat problem, a good problem in astronomy. No matter which direction you look, it seems like the Earth's the middle of the universe, but so are all other places. There's not like really a middle like that. Anyway, so these things become very disparate. There are 2 other phenomena that are good to know about. Let's see, 12. All right, we got like 13 minutes. There's 2 other consequences. There's a consequence called length contraction. And length contraction goes like this. Here's your spaceship, and here's a person on board the spaceship. And the person on board the spaceship would say, the length of my spaceship, when I take a ruler and measure it, I'll call that L sub p, is maybe like 30 meters. But if that spaceship is traveling along at some kind of velocity and somebody outside the spaceship is observing the spaceship, they'll observe the spaceship to be a different length. And the way that goes is, imagine the spaceship is coming toward you. As this spaceship comes toward you, you see the front of the spaceship. And it takes some time for the front of the spaceship to get to your eyes, but it takes a different amount of time for the light from the back of the spaceship to get to your eyes. You know?
6 feet. So.
Yeah. When you observe the world, when you listen to things and look at things, you're observing them as they appeared in the past and as they sounded in the past. If that makes any sense. It takes time for sound to get to you. It takes time for light to get to you. So when you look at the spaceship, not only does it take time for light to get from the spaceship to you, which is pretty close to 0 because light goes really damn fast, but it takes a different amount of time for the back and the front of the spaceship to get to you. And because the speed of the spaceship affects the relative times that it takes, you end up with different amounts of relative time. So I got the paper to give to you, but the person out here, it works kind of opposite. The person out here would measure a length, and that's equal to L sub p times the factor 1 minus v squared over c squared. And then there's a whole other thing, and it's related to this E equals mc squared thing. This is called the equivalence principle. Energy is equal to mass times the square of the speed of light. It's actually a separate paper from special relativity, but it's related in that, there's a law of conservation of matter and a law of conservation of energy, but Einstein's like, hey, check this out. They're actually one and the same. Energy and matter are equivalent to each other. Nonetheless, this spaceship also has a different relative mass. This spaceship has some kind of mass, maybe like 100 or 12,000 kilograms, and that's like a proper mass. But a person observing the mass of the spaceship, or the mass of the spaceship as a result of having a velocity v, is higher. So there's this thing called relativistic mass, and relativistic mass is equal to the mass divided by 1 minus v squared over c squared. This v squared over c squared is the time dilation factor, which depends upon the speed of the thing. So here's what's ingenious. Albert Einstein's like, listen, I know the definition of velocity, and I got myself the Pythagorean theorem. I'm just going to like whip up some Pythagorean theorem definition of velocity. And I end up coming up with this expression that relates the speed of things to the speed of light. And as a result of that, I conclude that the rate at which time passes is relative to the speed of the object. Because then everything can work out. Because when you're driving along in a car, the light goes out at the speed of light relative to you, and a person standing alongside the road would also agree the light travels at the speed of light. And the only way that that can be true is if the rate of passage of time is different for the two different people. This really only matters when you got to be doing, like, for it to really matter, like 7/10 the speed of light, 8/10 the speed of light, you know, yeah, real fast. So in your life, in the things you experience in your life, it's not a big deal. Like, if you become an airline pilot over the course of your life, you will have traveled at pretty high speed for like long periods of time, so that if you were to have an atomic clock with you and measure the cumulative amount of time, like, you're younger than you really are, you know? But the other problem is airline pilots have a slightly higher risk of shorter life due to the fact that you're higher in the atmosphere and therefore you have less radiation shielding from the atmosphere itself, which doesn't put you individually at a higher risk of it. Doesn't put all pilots at a shorter life risk, but because of the higher rates of radiation, it increases rates of cancer.
Dilation.
Yeah, well, so the problem is everybody on Earth is like, yo, man, you were born like 60 years ago. And you're like, well, actually, I was born like 59.99997 years ago, according to my clock. You know, so more time has passed on Earth than they thought it did. But anyway, so one of these problems, the first one is one there about like, what if you're on an airplane for 12 hours and you're going 260 meters per second? Like, how much different would the time be? So you put 260 meters per second in for V and 3 times 10 to the 8th meter per second in for C. But then anytime you do stuff in terms of the speed of light, it's smarter and easier to substitute the value for like the speed of light. This might sound like it's some kind of mumbo jumbo, like crazy hypothetical. This is not crazy hypothetical stuff. This is settled science for 117 years, and we rely upon this math to make sure. Otherwise, if Einstein had not proven this, and we came up with a concept for GPS satellites with precise atomic clocks and launched them into space, we would have been like, what the hell's wrong with these things? How come they keep falling out of whack? And it turns out in just a 24-hour period, the clocks aboard GPS satellites traveling at the speed they're traveling are lose enough precision to make it so that their location and time data is useless on Earth. This is absolutely settled, and I think you can see the reason why, like, somebody might say Einstein was bad at math, which is absolutely untrue, is that you start with the definition of velocity and the Pythagorean theorem, and that's it. There is no more math besides like a little bit of algebra. Like, it's unbelievable. And Einstein did some other great things, some very a lot of revolutionary things in theoretical physics. And actually, people argue that, well, so Einstein won the Nobel Prize in physics for the photoelectric effect, which, to be honest, I mean, everyone's opinion is a little bit different about this. It was kind of a stretch because Einstein was a theoretical physicist and not an experimental physicist. And the work that Einstein did isn't necessarily Nobel Prize worthy. But everything that he did was the most revolutionary physics that any physicist had done. Not only his individual accomplishments, but his cumulative accomplishments. It's like, how can you not give Einstein, be like, just do something, and we'll give you the thing. Yeah.
When we do the time, like obviously B and C are continuously given meters per second,
Mm-hmm.
and it gives us the time as hours.
Yeah.
Is that like, do we just keep it as is, or
It
do we
can-
have to change hours to seconds?
No, it can be hours because so this v squared over c squared is really just a ratio because if this is a meters per second, that's a meters per second. This is just a ratio. So then this time and that time, if they can both be in seconds, both be in meter or hours, both be in days, years, whatever. You know what I'm saying? So really, it's a time divided by a ratio or just a number.
How much it gives us hours, we want the answer in hours.
Hours is fine. Yep.
Maybe we can do a lab for this, meaning if the school were to have enough money to buy two incredibly precise atomic clocks and a plane ticket around the world.
Yeah, you kind of can't. The thing with the Keating-Hayfley experiment is it's both a test of special relativity and general relativity. And another thing is that the velocity is squared means that the direction doesn't matter. In other words, you fly around the Earth, you're like, well, you got half the velocities one way, the other half's the other way. Shouldn't they all cancel out? It doesn't work like that. It's the same as like kinetic energy, the velocity squared, so it's a scalar. So this whole denominator here is always a scalar. The inside the radical has to be positive, and it has to be a scalar value. Yeah, this is like really good stuff. This is beginning with about 1900. We call this modern physics. So to say modern physics is like 100 years old.
So
Yeah.
one reactor they had, it was like plasma suspended by magnetic fields. There's like one in Japan. It hasn't sustained itself under full power yet, but it's getting pretty darn close. Yeah, Photoelectric
Yeah.
reactor, I think.
So I'll give you some more examples tomorrow, but then those problems, work on them, and then today's Tuesday already, which is awesome. We'll go over those on Thursday, and we'll do some other problems tomorrow, and then I'll ask you some questions, maybe give you a problem or two to do. That'll keep us busy for this week.
So we're going over the
Isn't that great?
questions on the paper on Thursday.
Yeah, sure. Is that exciting?
Yeah,
Are you excited by this? I don't know.
You know, I see.
I like it.
I think it's cool.
And everybody who shares this proof always uses the train because that's what Einstein was like. I'm going to imagine him in a train car because in 1905 there weren't spaceships, there weren't really cars, there weren't
100
airplanes.
years later, there's the space shuttle
Yeah, I mean, like
lunar landing.
the Wright brothers were kind of sort of making stuff fly around, sort of, right?
It's off the ground.
I mean, even by World War I, we had
Motorized kites.
we had planes that were kind of ratchet. Yeah, paper covering wood, and they were like shooting revolvers.
Tossing bombs. Like
Yeah.
Throwing like lawn darts.
Yeah, just throwing stuff overboard. They'd put a bunch of rocks in their lap and go take off and then throw the rocks out and like shoot each other in dogfights.
Pages in their pistols to catch the rounds they wouldn't do.
Literally is like.
Hmm?
There's a reported instance of a guy who was parachuting, and he got a plane with his pistol while he was falling.
Nice.
He got the pilot.
And they made like the guns were feet on the front, so like it shoot only when the propeller
The
wasn't
timing.
in front of it.
Yep.
Well, I don't think
Even
that was-
that was used even up through World War II.
Yeah, it could've
Yeah,
been
and then
whatever.
so I mean, and then it didn't take long to figure out we can mount them on the wings. Then you don't have to deal with that. But the problem is when you mount the guns on the wings. I mean, that's where the fuel tanks are, and you got to have the ammunition out there. It's kind of inconvenient, but
convergence angles and stuff.
yeah.
When they converge.
But even like the B-17, the tail gunners, they had to make sure they didn't like shoot their own tail off, or the ball turret gunners.
Oh yeah.
They could have shot into the plane. There was nothing to stop you from
You turn around.
shooting
and
the
look
plane.
Up, it's like,
Yeah.
So
Yeah.
I find it funny.
Please on
Shoots
Thursday.
play.
I'm not gonna
Yeah.
be here on Friday.
That's cool.
Okay.
All right.
I could do after school if that would work.
Yeah, or during class, whatever. All
Kinda
right.
cool how these are so old. They're being used today, but they had tail gunners in their original form. Like,
Yeah.
it's crazy. 60, 70 years that plane's been in service.
I just saw. So they're gonna re-engine them, but I also saw a video where they're automating the crabbing for the landing and takeoff, and they built a prototype. So I don't know if in the B-52, you can steer all four wheels.
Yeah.
So when they land in a crab, they can
The
put
wheels.
in the
So they can
wheels.
just like,
Yeah, as they
Really like
land
that.
crab, the wheels are that way.
right?
They also do it during takeoff, but it's manually done. Like they have a chart that says, if
X crosswind, X angle for wheels.
yeah, it's like here's your uh, crosswind angle and crosswind speed, and it tells you the angle for the wheel.
Mhm.
But they're putting a new system in that is automated.
Yeah.
So it takes
Barometers.
it takes automated information and does the calculation for the pilot. And I saw they did a test, and they actually had a really high crosswind. It was Edwards Air Force Base. So there's cross runways, and normally you don't intentionally take off with a crosswind. You would
Yeah.
just switch runways.
Yeah.
Well, they just took off with a heavy
testing,
crosswind. Yeah, and it was amazing. The plane tracking
They're so
straight
big,
down.
They don't even like know that they just lift when they take off. I haven't seen one yet in person, but I've seen videos.
So the issue is that when you go down straight down the runway and there's a crosswind, you get different amounts of lift. You get more lift on one wing than the other in a crosswind. But when you crab in, you don't have the lift differential. You have the same lift on both of the wings, which helps. These also have those, the outrigger wingtip wheels.
How much
But-
does sag? Like when it's in flight, I don't think. Like, if they were perfectly rigid, I don't think it would need them. But I don't know.
Yeah, but part of it is that whenever you take off and land, and the wingspan is very long, they're fairly flexible wings, and they're pretty close to the ground. Especially the outboard engine nacelles could touch the runway.
How'd they catch the U2s had those, right? They had they would fall off when they took off.
Ye-
U2 had big old droopy wings.
Yeah.
Yeah.
Have you ever seen the video of that? Whenever they come to land, another pilot pulls in behind them with a car.
A truck, yeah.
Yeah, they usually.
It's like
I thought they use a car. Don't they use like a Corvette or something? Yeah, so they.
That would be like the most American thing ever, like catching a spy plane with a Corvette.
Well, so like as soon as they cross the threshold, then they turn onto the runway right behind them, and then just gun it.
Yeah.
And the person, I think that the driver of the car is also a pilot, and they're directly talking to the pilot on board the plane, and they talk them down. They're like 5 feet, 4 feet, because I guess from the windscreen you don't have a good view of the runway at all.
Have you seen the advertisement Toyota did with the early 2000s Tacomas or Tundras when they pulled the space shuttle?
Yeah.
They towed it. I have a bumper sticker that says "Honk if your car towed the space shuttle." It's a picture of the shuttle with Toyota.
Yep.
It's so cool. So we had a Tacoma for a while. We did not like it at all, but it was cool.
Cool.